All right, so as good afternoon. People still start trickling in. We're just gonna do a quick review before I give out the AC on a theoretical versus experimental probability question. Right, so I'm on page 35 here. So I have this question. Bradley spun the spinner 40 times and recorded his results in the table. Right, so right away for this one, I'm going to write, right? This is my theoretical information here, and this is my experimental information. Right, because in these questions, we're kind of dealing with two different, right? When we ask for theoretical probability and we ask for experimental probability, we've got to look at two different cases. Right, so for part A here, we have for a single spin, what is the theoretical probability of spinning green? Right, so theoretical probability of green for one spin, right? So we're not looking at his experiment that he did, we're just looking at the spinner here, right? So how many ways can we spin green? One, and there are four other possible spaces. Good afternoon. Right, so this would be 1/4 or 0.25 in decimal or 25%. Right, so the part B, for two consecutive spins, what is the theoretical probability of spinning red first and blue second? So this is actually a question that I'm going to skip part B for now, because it's actually a question that involves independent and dependent events. But it's a good question. I may come back to it if I remember, but just I don't want to do it right now because you're not going to have a question like this on your AC, so I don't want to confuse you when I go through it. So I'm just going to skip part B for now. So part C, according to the table, what was the experimental probability of spinning blue? Right, so I'm asking for experimental probability. Right, so I'm not looking at the spinner. Right, I am looking just at Bradley's experiment here. So experimental probability of spinning blue. Right, so that is, now I'm looking at the table, how many times did he spin blue? 12. Right, and he spun a total of 40 times. We're given that up here. So we don't have to sum these up. We're given the total this time. So the experimental probability is 12 over 40. Right, and if we plug that into, over 40, right, we plug that into our calculator and we want to convert it to decimal and percent. It's 0.3 or 30% exactly. Right, and just for a review, right, what would be the odds? So for part A, I'm just going to say here state probability as odds as well. Right, so if I want to state the probability, right, of 1 over 4, what is the odds of spinning green, right? So the odds of spinning green, right? It's the number of ways to spin green, right? And then it's not spin green. Right, so the probability would be there's one way to spin green, right? There's 3 ways not to spin green. Right, that's from 4 minus 1. So I'm minus, so really what I did here is just total minus 1. Right, and if I wanted to convert this experimental probability of spinning a blue, right? So 12 over 40, again, it's your desired event always goes first. So our desired event is to spin blue. And then, right, on the other side is always the opposite. So spin blue and not spin blue, right? So he spun blue 12 times. And the number of times he didn't spin blue, right, is 40 minus 12. So the odds of spinning blue is 12 to 28. And again, odds, right? The two numbers on each side of the colon should always add up to your total, right? So in this case, our total was 4 because we're looking at theoretical probability. And in this case, right, our total should add to 40 because we're looking at our experimental probability. Part D, according to the table, what color has an experimental probability closest to its theoretical probability? So we know the experimental probability of blue. Right, is 12 over 40. Let's calculate the other experimental probability. So the experimental probability of green, right, would be the number of times he spun green, which was 6, right, out of the 40 times he spun. Experimental probability of spinning a red, right, so he spun red 9 times out of the 40. And then the experimental probability of spinning a white, so he spun a white 13 times out of 40. So those are all our experimental probabilities. And we want to know what color had an experimental probability closest to its theoretical probability. Oh, that is not. Forgot a 0 there, 12 over 40. Right, so we know that the probability of spinning any of the colors, right, it's a fair spinner. Each space is equal in size, so the probability of spinning any of these colors is 1 over 4 for each of them, right? The theoretical probability is 1 over 4. Right, so if we want to find what is the closest color that has the experimental probability closest to 1 over 4. Right, well, what is 1 over 4? Right, so if we get these in similar, right, so we got to see, right, 1 over 4 is the same as 10 over 40, right? So we want to see which one is closest to 10 over 40, right? Because this equals 1 over 4, which equals our theoretical probability. So what color is the closest to the theoretical probability? Red. Yeah, so this is 12 over 4 or 12 over 40. So that's 2 over 40 away. This is 4 over 40 away. This is just 1 over 40 off, right? So this he spun it 9 times red, and we expected him to we we could have predicted for him to spin it 10 times based on the predicted the theoretical probability, right? And then white was 13 times, so a little further off from 10 than red, right? So the expected value, or sorry, I keep saying expected value. The experimental probability of red equals 9/40 is closest to, right, 10/40, which is the theoretical probability. Adjust the camera. Yes. Zoom in. Yes. Any questions on part D? All right, so part E. If Bradley spins the spinner 200 times, how many times would you predict the spinner lands on green? So he's going to spin it 200 times. How many times would you predict the spinner lands on green? Right, so this is a prediction question. We want to predict how many times the spinner lands on green. Right, so I'm going to write out my prediction formula here. Right, so my prediction. So we are given experimental, so we're dealing with experimental probabilities and theoretical probabilities. If we want to make a prediction, what probability should we always use when we're given both? Theoretical. Yeah, we always want to use the theoretical probability. So that, and we want to predict how many times he spins green. So it's the theoretical probability of spinning a green times I'll write out the formula. So 200, but 200 is our sample size, right? That's how many times he's gonna spin it, right? So the theoretical probability of green, we calculated it up here, is 1/4, right? So it would be 1/4 times our 200 times that he's going to spin it. If we plug that into our calculator, it will give us 50. So we predict that he will spin green 50 times if he spins the spinner a total of 200 times. Right. So make sure, because the theoretical probability of green is 1/4 or 1/4. The experimental probability is 6/40. Right. So these two are not equivalent. So make sure you always use your theoretical probability when given both. Part F is an explanation question. In your own words, what is the difference between theoretical probability and experimental probability? So theoretical probability is what is what we expect to happen or should happen, right? If we flip a coin, right, we expect that there's a 50% chance that it either lands on heads or lands on tails. So if we flip a coin twice, we expect, or we would predict that one time it would land on heads, one time it would land on tails, right? That's what should happen. So theoretical probability is what we expect to happen or should happen, right? So again, theoretical probability, let's say an event, right, is the number number of ways so event E can happen over total number of outcomes. Right? An expected probability or experimental probability is what actually happens in an experiment. Right? So it's based on trials, we can say. Right? So theoretical probability is what we expect to happen, but if we did an experiment, right, if I actually flipped a coin twice, then and I got heads both times, right, then the experimental probability of getting heads would be 100% because both times I flipped a coin, it landed on heads, right? So experimental probability is what actually happens in an experiment, right, based on trials. So if we wanted to write that formula, again, it's very similar. Experimental probability of an event E. So I just want to see, just to keep it consistent, I believe it's written, right, favorable events over a number of trials. So the difference here is, right, we're dealing with trials. Theoretical probability, we're dealing with possible outcomes. Right, so number of all over total number of trials, right, or times, right? In this case, our trials was how many times he was spinning the spinner. So we did 40 trials of spinning the spinner. So that's kind of the so they're similar in terms of their the way they're defined algebraically in terms of an equation, right? But experimental probability is based on what actually happens in an experiment. Theoretical probability is what we expect to happen. All right, any questions before I give out the AC? So the AC is only on theoretical and experimental probability. All right. So we're going to be a couple of questions in here, but that's okay. So now we want to calculate the theoretical probability of rolling a 2. So we're not looking at the table. We don't use any of this information because it's based on this is his experiment. We want theoretical probability of rolling a 2. Yeah, right? So how many so we're rolling a 4-sided dice. How many possible ways can you roll a 4? Right? There's only one way you can roll a 4. And there's 4 sides. So the theoretical probability would be 1 over 4. Experimental probability of rolling a 4, right? So now we just do the same thing. We're looking at the experiment, so we're looking at the table. How many ways did he roll? How many times did he roll a 4? 535 times out of the 1,800 times he rolled. The theoretical probability of rolling a 4, right? So how many possible ways can we roll a 4 on a 4-sided dice? 1, right? There's only one side with a 4, and there's 4 total sides. State the experimental probability of rolling an odd number. So the experimental probability of rolling an odd number, right? So that an odd number, in this case, right, we're only going up to 4, so it's 1 or 3. So the experimental probability of an odd number. So how many times so it's either a 1 or a 3. How many times did he roll a 1? Right, 410 times. And how many times did he roll a 3? 460 times. Right? So you can roll, we want the probability of rolling either a 1 or a 3. So it's 410 plus 460. Right? So that gives us 870 over 1,800 for our experimental probability. For our theoretical probability of rolling an odd number, right? So again, it's a 1 or a 3. Well, you can roll a 1, you can roll a 3, so that's 2 possible ways to get that event over 4, right? And again, if you reduce, that's fine. If you switch to decimal, that's fine. I didn't ask you to, but right, if you still got just looking for the non-simplified fraction. So part G, state the experimental probability of not rolling a 3. The experimental probability of not rolling a 3. So now our desired event is not rolling a 3. So how many, and we want the experimental probability, so I'm looking at the table. So how many times did he not roll a 3? Well, I can just add up 410 plus 395 plus 535. That's how many times you rolled a 1, how many times you rolled a 2, how many times you rolled a 4. And then this is divided by 1,800. Right, so if I plug that into my calculator quick, what do I get? Right, 1340 over 1,800. Right, so that's my experimental probability. Theoretical probability of not rolling a 3. Not rolling a 3. Well, how many ways can you not roll a 3? 3 ways, right? You can either roll 1 of 2 or 4. And there's 4 possible sides on the dice. So that would be my theoretical probability there. Part J, what could John do to bring the experimental probability results closer to the theoretical probability? Right, so again, if we want, so there's a little diagram in your notes that kind of that summarizes this concept well. Right here. Right, so a small sample space or a small number of trials. There's multiple ways to say this. Right, so a small sample space. So if I roll a dice not that many times, my experimental probability and my theoretical probability will not be that close. But a large sample space, so if I roll a dice thousands of times, I can expect my two probabilities to be close. So what can he do to increases, how is it worded? So as experimental results are closer to the theoretical results, what can he do? So John can roll the die right, more times. Right, or in other words, he can increasing his sample space. Increasing the size of his sample. So each one on this page is just worth 1 mark. You can total up, right? So 1, 2, 2, 4, 6, 8, 10. There's a total of 11 on this page. And then on the back page, part 2, or question 2, Sylvia is spinning the wheel depicted. She spins 30 times. And recorded the results. So again, I'm just going to quickly write. This is my experimental results. These, or I look at the actual wheel or spinner for my theoretical results. So state the probability of the spinner landing on purple, right? So theoretical probability of landing on purple. How many ways can it land on purple? So it's theoretical, so I'm looking at the wheel, right? There's 1 space with purple, so it'll be 1 over how many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8. There's 16, right? 16 spaces. Right, so it's 1 over 16 would be the theoretical probability there. Experimental, now I'm calculating the same thing, but now I'm looking at Sylvia's experiment. So now I'm looking at how many times did she spin a 3? Or sorry, did she spin a purple? 3 times, right? 3 times. And how many times did she spin it? 30 times. Probability of a spinner landing on green, right? Same thing. How many greens are there? 1, 2. There's 3 spaces of green out of the 16 spaces. For the experimental, I'm looking back. How many times did Sylvia spin green? 9 out of 30 times. Watch the wording here. So now I've been asking about probabilities. Now I want to ask, state the odds of the spinner landing on purple. Right, so we calculate the probability, the odds of the spinner landing on purple. So I state my desired event first. So how many ways can we land on purple? Theoretically, we're looking at the spinner again, right? 1 way. How many ways can we not land on purple? Right, that's 16 minus 1, our total minus 1. So that gives us 1 to 15 is our odds, our theoretical odds of landing on purple. Our experimental odds, right? So it's the same procedure. Now we're just looking at the table. So how many times did we get the desired event, which is spinning on purple? We got it 3 times. How many times did we not get purple? Or did Sylvia not get purple? 3 minus 30 times, right? So our odds would be 3 to 27. So I'm back to probability now. State the probability of the spinner landing on yellow, right? So theoretical, I'm looking at the spinner. 1, 2, 3, 4. There's 4 spaces out of 16 are yellow. And for the experimental, how many times did she spin a yellow? 7 out of the 30 times she spun a yellow. Probability of spinner not landing on yellow, right? So we can either use this answer or we can just use the table, right? But the theoretical probability, right, would be 16 minus 4, right? So that's not landing on yellow over 16. So it would be 12 over 16. Oops. That we don't land on yellow. And for the experimental, right, it would be 30 minus 7 over 30, which gives us 23 over 30 ways of not landing on yellow. And then for part F, we are back to odds. State the odds of the spinner not landing on purple. Right, so now I calculate the odds of the spinner landing on purple, so now I'm just switching these. Right, so the odds of the spinner not landing on purple is 15 to 1. And the experimental odds is 27 to 3. And then for here, right, theoretical, how many ways can we land on blue? 1, 2, 3 out of the 16 times. And Sylvia spun it 5 out of the 30 times. Right? So for part 3, Lisa rolled a 6-sided die 25 times. She rolled a 3 on 8 occasions. State the theoretical and experimental probability. Well, the theoretical probability of rolling a 3 on a 6-sided die, well, we can only do that one out of six ways. Right? There's only one side with a 3 on it. The experimental probability of rolling a 3, well, she rolled 25 times and she rolled a 3 on 8 occasions. So 8 out of the 25 times Lisa spun or rolled a 3. Is the experimental probability accurate? Right, so this is asking how close are these? So for this, you want to, since they're not under the same denominator, it's easier to convert to either percentage or decimal. This should be a 7, right? And 8 divided by 25, so 0.32. So we can see that the experimental probability is almost doubled of the theoretical probability. So is the experimental probability accurate? No, right? It's almost double, not accurate. What should Lisa do to be more accurate? Right, to be more accurate, Lisa should roll the dice or the die more times, right? Or increase her sample space. So each one of these on the back side is 2, so 2, 4, 6, 8, 10, 12, 16. 16 on the back, just to make it equal to what was on the front. So 11 on the front equal 16 on the back. So you can add those up and pass them to the front. Sorry? 1 second.